Yeah.
Okay, yeah. So I want to talk about my work joined with Florian Naef, that's on archive, and the general topic is string topology. Um, Namely, we want to understand homotopy invariance of string topology operations. So let me just introduce, what string topology is and what I mean by homotopy invariance. So let's say you have some manifold, and let's just say it's closed and oriented for simplicity, M. So you have various operations on homology and cohomology. The main operation I'll care about is what's called the intersection product. So this operation, it's just Poincare dual to the usual coproduct on cohomology. So there's a coproduct on cohomology which preserves degrees. And then if you apply Poincare duality, it will shift degrees on homology. So you get this intersection product. If you're in, if you look at homology classes and complementary dimensions, and if they're suitably transverse, then this is literally given by intersections of the corresponding classes. Okay, so you have this intersection product, which is given by intersecting submanifolds. So a priori, if you think of that in terms of intersecting submanifolds, it's unclear if this is actually invariant or homotopy equivalences of the manifold. To even formulate this question, to say that this product is homotopy invariant, you have this shift by D. So first of all, you want to know that the dimension of a manifold is homotopy invariant. So if you have two homotopy invariant closed-oriented manifolds, then their dimensions are the same. Okay, so that's a true fact. And then the claim of homotopy invariance is that, if you have any homotopy equivalence of manifolds, then the two intersection products agree perhaps up to a sign, and the sign has to do with orientation. So homotopy equivalence might reverse orientations. Okay, so the claim is that there's this commutative diagram. Okay. And so that's the kind of homotopy invariance property I want to understand for string topology operations. So there will be some operations on homology of the manifold or homology of its loop space. And I want to understand a similar kind of commutative diagram, whether it holds. Okay. So let me talk now about string topology. So I will not say much about string topology. It's a big topic. Namely, the idea is that you want to enhance this intersection product, which was on homology of, so there was an intersection product on homology of the manifold. You want to lift this to a kind of intersection product on homology of the loop space. So this LM is the space of loops in the manifold. Okay, and besides just this intersection product, there's a bunch of operations. I'll just mainly be talking about two. So one of them is the loop product. And this is completely analogous to the intersection product on homology. Just it's kind of intersection product homology of the loop space. So this was introduced by Chas and Sullivan. And then there's another operation, which is kind of coproduct type operation. And that operation has a few subtleties. So the first subtlety is that it's not just the usual homology, it's relative homology. So you look at homology of the loop space relative to constant loops. So instead of loop space, you have the subspace given by constant loops. And so you have this kind of coproduct type operation. And the second thing to say is that this loop coproduct, there's a shift by D-1 as opposed to the one in the product, which has just a dimension. Okay, so these are the main two operations I'll be talking about, the loop product and the loop coproduct. So let me say some results about these. If you look at this loop product, it's actually a part of some two-dimensional TQFT, so topological quantum field theory. Namely, it's the kind of pair of pans product in a TQFT. So if you look at, so it's a 2D TQFT. To the circle, you associate homology of the loop space, and to this pair of pans, you associate the loop product. And actually, this whole TQFT, this TQFT was defined by Cohen and Godin, is homotopy-invariant. And in particular, this loop product is homotopy-invariant. Again, there's an issue with orientation. The corresponding diagram, if you have homotopy equivalent manifolds, commutes up to a sign. But the goal of these operations, it's not just to define some random operations on homology of loop space. The goal is to study manifolds and their smooth structure. So actually, the reason Chas and Sullivan introduced these is that they use some subtle intersection theory to define these operations. And the hope was that these operations are not homotopy-invariant, so you can see something about the manifold rather than just the homotopy type of the manifold. Okay, so there was a there was kind of a negative result that the loop product is homotopy-invariant despite the complicated original definition. And what we prove is that the loop coproduct, so essentially the first result of its kind in string topology, that the loop coproduct is not homotopy-invariant. And in fact, we sort of write a precise transformation formula that I'll be talking about later, like how it fails to be homotopy-invariant and what exactly it captures from the manifold. Okay, and one of the reasons is that it sees a little bit more than just to define this loop coproduct. You don't just need the TQFT, you need what I call compactified TQFT, and I'll say a few words about that later. So that's the main result that I'll be talking about. So the idea is that there will be some two-dimensional TQFT in the background, the string topology TQFT. And that TQFT only sees the homotopy type. So actually it's depends on the category of local systems on this manifold. But because this loop coproduct is not just an operation you see in TQFT, it's an operation you can see in compactified TQFT, you need extra structure. And this extra structure depends on what's called the simple homotopy type of the manifold. And so that's the extra bit that this loop coproduct will depend on. And then transformation property will involve how this simple homotopy type changes. So my goal is to explain all of these notions. Okay, so before I go into any of the details, are there any questions here?
Yeah, so the homotopy invariance here is similar to the diagram you showed, like M changes from M1.
Yeah, literally that kind of diagram you want to know. And as I said, for the loop product, if you put the loop product here, this diagram commutes up to a sign. And if you analyze a similar diagram for the loop coproduct, the claim is that it does not commute. There's a correction factor.
Okay. And what was the original motivation of Sullivan along these lines? The idea is sketched here, just the things depend on simple homotopy. So
he didn't talk about simple homotopy types. He didn't know that what they exactly depend on. So the hope was that they depend very strongly on the manifold. Precisely which aspect of the smooth structure, it wasn't clear. As I said before, a few years ago, there wasn't a single example of a string topology operation that was known to be not homotopy-invariant.
Okay. Mhm.
Okay, any other questions? Right. So let me. So I will not define this loop product and coproduct in details. What I want to explain is kind of a precursor to these operations in the case of surfaces. So there's a very concrete way to describe analog of these loop products and coproducts in the case of surfaces. So let me describe these operations. Okay, so in this case, my manifold is a surface. You have some oriented surface. And you look at this free vector space on a homotopy classes of loops on the surface. So you can imagine literally you have loops on the surface. And on this vector space, there is a Lie bracket, which is called the Goldman bracket. So if you imagine two loops on the surface, they will generically intersect. And then the way you compute the bracket, if you have two loops, alpha and beta, is that you sum over all intersection points. And yeah, it's the sum over intersection points of ways of resolving. So basically, you want to take the union of these two loops based at the corresponding point. So here I've resolved the bottom point, and here I've resolved the top point. And the way you resolve the points, so for that, you use orientations. I will not be precise, and then there's some signs insert. Okay, so and the claim of Goldman is that this actually gives a Lie algebra structure. If you've seen this Goldman bracket, you might have heard about a connection between the Goldman bracket. So the reason Goldman chooses this bracket is that it relates to what's called the idea-bot. So it's an explicit way to compute this idea-bot symplectic structure on character varieties of surfaces. So let me just write the simplest character variety, let's say GLN character variety. So if you look at representations of the Van group into GLN, modded out by GLN, on the smooth locus, there's a natural symplexic structure. And Goldman tried to write the corresponding Poisson structure in explicit terms. And if you have a loop, you get a function on this representation space given by the holonomy of the local system around this loop. So it gives you a trace of the holonomy. It gives you a function, and he was basically trying to compute the Poisson bracket of these functions. Turns out the Poisson bracket of these functions has a very easy kind of combinatorial description. Okay, so that's the Goldman bracket, which is analogous to the loop product. And there's also a co-bracket analogous to the loop coproduct operation. It's the following. So it was introduced by Turayev, and there are some subtleties. So first of all, you mod out, you don't just look at the space of loops, you look at loops mod constant loops. And then you have a co-bracket, which is defined similarly, except you split the loop at the self-intersection points. So here I have the figure 8, which I think of as a single loop on the surface. and it has an intersection point, self-intersection point, and you split that into the individual loops alpha and beta. Okay, so if you look at this operation, if you're just trying to see if this is well defined, well, you encounter a problem of the following kind. If you just imagine a twist in the loop, you can just imagine a homotopy where you straighten the loop and the twist disappears. And if you apply the cobracket to that, on the left you pick up an extra term, which is that constant loop, and on the right you don't see that. So for this operation to be well defined, you mod out by constant loops.
So how does the constant loop arise on the left?
So there's a self-intersection point. Like let's imagine that this is maybe closed. This is alpha and this is beta. So there's a self-intersection point. So according to this rule, you would pick up alpha tensor beta minus beta tensor alpha. And on the right, well, maybe there's more intersection points somewhere. On the right, you don't have that contribution of beta. So basically, you want to kill off this extra term on the left-hand side. On the right-hand side, if this is really closed, like this, you get 0. Because you don't have any self-intersection points.
Oh, okay.
And so for this operation to be well defined, you just mod out by contractible loops. Yeah, so the only problem is in contractible loops, so you mod out by those. Okay, so the theorem of Turaev is that it actually defines an interesting algebraic structure on the space. So you had a Goldman bracket, which is a Lie bracket, and this is a co-bracket. So in total, you get a Lie bialgebra. It's called Goldman-Turaev Lie bialgebra. Another way to think about this problem with constant loops is that if you thought about knot theory, you know this move is called the Reidemeister 1 move. And this Reidemeister 1 move changes the framing. So if you think of these as framed knots, this changes the framing. So one way to fix this problem, instead of modding out by constant loops, what you can do is choose extra structure on the surface, for instance, a non-vanishing vector field. And then you basically compute rotation numbers of the loops with respect to that vector field. And then the rotation numbers of the two sides will be different. There's like an extra rotation of the loop. So basically adding an extra term is given by the rotation number, you can also fix this problem with the fact that it's not well defined. So there's two ways to fix this problem. Either you look at something mod constant loops, or you look at extra structure. Okay, and the upshot is that you look at this vector space. So this vector space G, one way to think about this is that you look at homology of the loop space. To connect to string topology, you look at S1 equivariant homology of the loop space, of the free loop space. And then this G bar is relative homology of the loop space. And so these loop products and coproducts descend to these operations, which are Goldman and Turaev Lie bialgebra. In this case of surfaces. Any other questions here?
So this also extends to the representation spaces of these representation varieties that you mentioned.
So the Goldman bracket captures the Poisson bracket of the representation varieties. The Trive co-bracket, the geometric meaning of the Trive co-bracket is somewhat subtle. You can relate it. So not in the case of GLN, but if you look at some supergroups, you can relate it to some BV structures. Yeah, so if you just look at the usual representation variety, the meaning of the Trive co-bracket is so you don't see the Trive co-bracket there.
Okay.
Okay. All right, so let me now go to the general setting of string topology. And I want to discuss the corresponding TKFT, the two-dimensional topological quantum field theory. For me, this topological quantum field theories will be some symmetric monadal functor from cobordisms, from the category of cobordisms to some target. There's some symmetric monadal category as the target. I'll be looking at extended two-dimensional TKFTs. So these are extended two-dimensional TKFTs. And for extended two-dimensional TKFTs, there's a fact which is called the cobordism hypothesis that says that they're uniquely determined by what you assign to the point. So if you specify some algebraic data, which is the value of the TKFT on the point, you can reconstruct the TKFT. In my setting, I'm going to look at the target being the two category of DG categories. So usually for in extended TKFTs, you look at some class of categories as the target. In physics terms, it's called the category of branes. And so you need to specify this value in a point, which is a category. So in my case, it's a DG category. In general, there's a lot of finiteness conditions you have to assume for this category to get an extended 2D TKFT. I will be looking at a slight variant of extended 2D TKFTs, which was introduced by Cohen and Godin. So these are called non-compact extended 2D TKFTs. What this means is that you can look at the cobordisms, but whenever you have an outgoing boundary, so if you have a picture like this, I'm going to read from bottom to top. So for instance, this picture is not allowed. Because you have an empty outgoing boundary, but this picture is allowed. So you have to have a non-empty outgoing boundary. So these are called non-compact 2D TKFTs. Algebraically, what this means is that it allows us to relax the finiteness conditions on the category to define this TKFT. And the relevant finiteness condition of the category is what's called a smooth DG category. So if you have any smooth DG category, the cobordism hypothesis allows us to define this non-compact extended 2D TKFT. Okay. So let me just go through some examples of smooth DG categories and so what the corresponding 2D TKFTs are. So you can look at the algebraic setting, you look at smooth algebraic variety, you look at perfect complexes on the smooth algebraic variety, and that's an example of a smooth DG category.
May I ask a question before moving on? I couldn't understand the non-compactness thing. Like, how is it related to compactness, the outgoing boundary being non-empty?
It's a term that was introduced in Lurie's work, it doesn't mean that something is non-compact. So maybe it's not the best terminology, but so all manifolds are compact. They have boundary, and so in a cobordism, you usually think that you have some incoming and some outgoing boundaries, and you don't allow empty outgoing boundary. So that's just the kind of cobordisms you consider.
Okay, just a
sorry, can you say again?
It's just a terminology.
Yeah. Cohen and Godin called it positive boundary to DHKFT. Okay. Yeah, and so yeah, we want to consider this non-compact 2D HKFTs. These are the ones relevant for string topology. Okay, so there's one example of 2D HKFT you get of this kind associated to smooth algebraic variety. So if the variety is smooth and proper, then you get a full extended 2D HKFT, not just non-compact. So that's called the B model usually. And there's a symplectic version of this. You look at some Liouville manifold, and you look at the Radfoucault category. Then this category is smooth under some assumption. And so that's called the A model, the corresponding to DHKFT. And then there is the string topology setting, which is what I care about. So this one is string topology. And this is where you look at a topological space and you look at local systems. When I say local systems, I mean local systems of chain complexes. So yeah, you look at the category of local systems of chain complexes on this topological space. And if the topological space satisfies some finiteness assumption, in this case, it has a homotopy type of a finite CW complex. So for instance, closed manifold. Then the corresponding category will be smooth. So that's the setting that's most relevant for my talk. So the upshot is that you take any of these smooth DG categories, and the convergence hypothesis produces for you a two-dimensional TQFT out of that. So the value on the point, the value of this function on the point will be the category itself by definition. And the value on the circle is the Hochschild homology of this category. And so if you think about this kind of pair of pans, this gives a product on the Hochschild homology of the category. Okay. All right, so that's something you can do in any 2D TQFT. Now, I want to talk about this sort of compactified aspect of a 2D TQFT. And for this, let me just look at a specific cobordism, which is this sort of elbow type cobordism. If you think about this operation, it has empty incoming boundary and two circles as the outgoing boundary. So this will give you some class in Hochschild homology of C, tensor Hochschild homology of C. One way to think about this is that if you have what's called a module of a DG category, you get a class in Hochschild homology. And in this case, the module is just a hom complex. So it gives you a class in this Hochschild homology of C, tensor Hochschild homology of C. Okay, and what's going to be relevant for the loop coproduct is an extra structure. And the extra structure is a null homotopy of this class. So this is a class on the chain level. And I'm going to choose what's called the Euler structure That's a null homotopy of this class. So bounding chain for this class. And then I want to understand how various choices depend on that extra choice. Okay, so that's sort of general introduction to these non-compact 2D TKFTs. So what can you do with this sort of elbow cobordism trivialization? Well, okay, so first of all, yeah, if you look at the pair of bands, you get a product with function homology. So that's great. And that's similar to the loop product operation. Now let's try to write the pair of bands upside down. And you might imagine that the loop coproduct relates to the upside down pair of bands. That's not quite right. And let me just explain what it actually relates to. So if you look at this upside down pair of bands, you can do the following operation. You can take this bit and pull it down. So this is what happened on the left. I took one leg of the pair of bands and I pulled it down. And if you look at the picture on the left, the way it looks like is it looks like a pair of pants. And to that, you precompose this pair of pants with this elbow cobordism. So that's the thing on the left. And on the right, you can do the same thing, but on the other leg. So you pull down the other leg, and then in total, you get a pair of pants composed with the elbow on the other leg. Okay. But now, okay, so that's just some random homotopy. You can't really extract anything out of that. But if you have an Euler structure trivializes this elbow cobordism, so these bits. So this tells you that if you have an Euler structure, you get a homotopy from 0 to 0. So that's a secondary operation. And in this case, you get this operation, a coproduct type operation on functional homology, except there's a shift by 1 because it's a homotopy from 0 to 0. Okay. So this is something you can do for any smooth DG category with Euler structure. You get these operations. So the natural question is what these operations are in some example. So for instance, in string topology, whether these are really the loop product and coproduct. The claim is that indeed this is true. So let me state this precisely, what I mean by that. So yeah, if you have closed oriented manifold, that's the setting where you have string topology operations. You look at functional homology of this category of local systems. First of all, you get homology of the free loop space. So that's the source of where the string topology operations live. And the first claim is that the first operation is the loop product. The second operation, it depends on the choice of the Euler structure. So what we do is we provide explicitly, we explain what is this choice of the Euler structure. And with that choice, we explain that you get the loop coproduct. Okay. So the upshot of this is that you have this TKFT, which just depends on the homotopy type of M, so completely homotopy invariant. The loop product is just obtained from the TKFT, so it's homotopy invariant. The loop coproduct depends on this extra choice of the Euler structure. And to understand its homotopy invariance, you just need to understand how this extra choice depends, how it changes under homotopy influences. So that's going to be the second main result. How this trivialization of the elbow cobordism changes under homotopy influences. Are there any questions so far?
Yeah, I'm a bit confused. So the Euler structure, does it come in when you construct the map in number 2 using these cobordisms, or does it come in the lift part?
So the Euler structure is giving you these extra. So you can always write these homotopies without extra choices, but the endpoints of this homotopy are themselves homotopic to 0 via the Euler structure. So that the Euler structure is what allows you to remove any elbow cobordism from any picture. So you see at the endpoints, you have the elbow cobordisms. The Euler structure tells you it's 0. The only thing is that here I'm looking at homotopy, so I need to keep track of that choice. And I do that at the left-hand side, like at the leftmost cobordism and at the rightmost cobordism. And then in total, I get a homotopy from 0 to 0. Yeah, without this choice of an Euler structure, you just get a homotopy from something to something.
Okay. And for the relative part, so this home class, how is that used?
So the home class is the value of the elbow.
Oh, okay.
And the Euler structure is what trivializes this class, or it's like by definition the trivialization of this class, the elbow.
Okay, thank you.
Yeah. So the only subtlety is that it's not trivializing to 0. So I mentioned that the loop coproduct is on relative homology, and so this Euler class, this home class is not trivialized to 0, but it's trivialized to constant loops. But that's sufficient to get operation on relative homology. Okay. Okay, so let me just before I get into this simple homotopy theory, I just want to explain these kind of Euler classes that appear here. So if you have a topological space, something you can do, you can try to take its Euler characteristic. Of course, the Euler characteristic is not defined unless you have some finiteness, because you look at the alternating sum of dimensions of cohomology groups, and you want to know that cohomology groups are 0 outside of some range, and they're all finite dimensional. So yeah, you need some kind of finiteness condition. One finiteness condition that's going to be relevant here is that you have a homotopy type of a finite CW complex that ensures that the Euler characteristic is well defined. Okay, so you have this Euler characteristic, which is a number associated to a manifold. There's a slightly better object, which is called the Euler class. So usually people consider the cohomological Euler class. This depends on the choice of an orientation. And for a manifold, it's a class in the top dimensional cohomology. And it depends on the choice of orientation. But there's a easier homological Euler class, which doesn't depend on choice of orientation, and it just lives in the 0th homology of the manifold. And these two classes are just Poincare dual. So 0th homology is isomorphic to the top dimensional cohomology. Okay. So these are sort of fairly classical objects. Now, if you look at sort of the theory of traces and dimensions in category theory, what you encounter is not the homological Euler class, but a version of this class on the loop space. So actually, it turns out that most naturally in string topology and things like that, you kind of get an even fancier version of the Euler class, which is a class that lives in the zeroth homology of loop space. Okay, so the loop space projects onto the manifold. Just you can, if you have a loop, you can evaluate this at a base point of the loop, and you get a point on the manifold. So you get this push forward map from homology of loop space to homology of the manifold. And then you can also, if you have a homology of the class and homology of the manifold, you can just integrate of the manifold and you get a number. And so you get Euler characteristic of the manifold, which is a number. You have this Euler class, which is class in homology, and you have this loop Euler class in homology of the free loop space. Okay. So this is some canonical things you can define for any topological space, and with some finiteness condition. And so then you can try to compute what the elbow cobordism is in string topology. And what you encounter is that so this cobordism gives you an element of homology of loop space tens of homology of loop space. So a zeroth homology class on LM cross LM. And what you can easily compute is that this is actually just the push forward of this loop Euler class under the diagonal. So the loop Euler class lives on in the loop space, and this elbow cobordism lives on loop space, product loop space. Okay, so that's the computation. And now the goal is to produce an Euler structure. And what this means, so let's forget about for a second about this diagonal. What this means is that you want to know that this class actually comes from constant loops. So there was loop space, it projects to M, but then also M maps to the loop space via constant loops. And you want to know that this homology class, which lives on the loop space, is actually concentrated only on triple loops. Now you can ask about Dyson law of homology. That's just a property. But for what I'm talking about, you need to find a null homotopy. So you need to find this lift on the law of chains. And so in the paper, we basically explained that if you write down some models of intersection product, or if you're familiar with this, you need what's called the Petrarchan-Thom collapse map for the diagonal to write intersection product. In models, this loop Euler class actually lifts to homology of the manifold. So it only lives on constant loops. Or in other words, it's trivialized in relative homology. Okay. So the upshot is that using intersection theory, there is a canonical Euler structure, mod constant loops. And so to understand homotopy-invariance property, you want to know the following thing. If you have a homotopy equivalence of two manifolds, for each manifold, you have this sort of intersection product and trivialization of the loop Euler class. And how do these two differ if you for two manifolds? So you can have two non-diffeomorphic manifolds, which are homotopy equivalent. And so you want to know how the two trivializations change under this homotopy equivalence. And so you get some discrepancy because you have two null homotopies in chains. You have some discrepancy in the first homology of the free loop space, rel constant loops. So out of homotopy equivalence, you get this class in the first homology. And basically, you want to know what that class is. And so that's the core computation, sort of trying to understand what that class is for homotopy equivalence. Okay. Any questions before I get into simple homotopy theory? Okay. So to explain what this class is, so it's going to be expressed in terms of what's called the Whitehead torsion. Let me say a few words what kind of object that is. So if you think about homotopy theory, if you think about homotopy types, you usually think about CW complexes up to homotopy cones. What I want to explain is what are simple homotopy types. And simple homotopy types will be given by finite CW complexes up to simple homotopy cones. That's one model of simple homotopy types. Okay, and so what is simple homotopy cones is the following gadget. So if you have two finite CW complexes and you have some homotopy cones between them, you can define an algebraic invariant of this homotopy cones, which is called the Whitehead torsion. So this Whitehead torsion lives in some Whitehead group of the fundamental group. So it only depends. So this group only depends on the fundamental group of the manifold. And the Whitehead group is a quotient. If you're familiar with algebraic K theory, it's the quotient of the first algebraic K theory of the group algebra, modulo its units. So you have units in Z, which are plus minus 1, and you have units in the group algebra coming from the group itself. Okay, so that's called the Whitehead group, and in the Whitehead group, you have what's called the Whitehead torsion. Okay, so yeah, you have some group, and you have torsion in that group, and then a homotopy cones is called simple if it has trivial Whitehead torsion. Okay, so that's just some property of homotopy cones of finite CW complexes. So you can think about various weakenings of the notion of homotopy cones. Maybe the strongest notion you can think about is a homeomorphism. Homeomorphism by a theorem of Chapman is a simple homotopy cones. And then a simple homotopy cones is a homotopy cones. Okay, so you have these sort of various notions of sameness for topological spaces. If you look at manifolds of dimension at most 3, turns out that simple homotopy cones implies homeomorphism. So if you have 2 manifolds of dimension at most 3, then they're simple homotopy cones if and only if they're homeomorphic. In fact, this whole theory of torsion originated with the Reidemeister in France, who classified 3-dimensional length spaces. So you might know that if you look at 3-dimensional length spaces, they're parameterized by these 2 numbers, P and Q. But there are some non-trivial homotopy equivalences between length spaces. For instance, I'll mention this in a second. L71 is homotopy equivalent to L72, but they're not homeomorphic. And the discrepancy was identified by Reidemeister in terms of what's called Reidemeister torsion, a precursor to Whitehead torsion. But basically, you have these 2 length spaces which are homotopy equivalent, but they're not simple homotopy equivalent. Okay.
Again, sorry, they are diffeomorphic, but not simple homeomorphic, or what? There is simple homotopy equivalence between this?
So they're not. There isn't a simple homotopy equivalence, and there is no homeomorphism. So they're not homeomorphic. Homeomorphism and simple homotopy equivalence in dimension 3 is the same.
Yeah.
So they're not the same. They're not homeomorphic, but they're homotopy equivalent.
That's something I'm sure. Okay.
And yeah, there's some explicit algebraic formula in terms of P and Q when two length spaces are homotopy equivalent. Any other questions? Okay. Yeah, so let me just finally get to the main result. So what is this discrepancy and what the loop coproduct depends on? So the claim is that if you have a homotopy equivalence of closed manifolds, then the two Euler structures, so the trivializations of this loop Euler class, differ by the trace of the Whitehead torsion. So the Whitehead group is was some quotient of K-theory group. And K-theory group has what's called the Dennis trace to Hochschild homology. So there's a trace map from the Whitehead group to homology of the free loop space. It's kind of, there's a lift of this. So there's a Dennis trace map to homology of the loop space. And so if you have a class in the Whitehead group, if you take its trace, you get a class in homology of loop space relative to constant loops. And the main computation is that that's the discrepancy. If you have a homotopy equivalence of closed manifolds, these two trivializations differ by the trace of the Whitehead torsion. So in particular, if the Whitehead torsion, so if the homotopy equivalence is simple, the Whitehead torsion is 0, this class is 0. Which means that if you have a simple homotopy equivalence, the loop coproduct will be the same for the two manifolds. And so Florian has computed explicitly loop coproducts for these two length spaces, L71 and L72, and just explicitly saw that these loop coproducts are different, and that there was an extension of this result by Naef, Rivera, and Wall for more general loop spaces, length spaces. So just seeing that this loop coproduct genuinely depends on this Whitehead torsion. Okay, so I'll stop here. Thanks.
Okay, thank you very much, Pavel. So any questions for Pavel? Well, I have one question. So the proof of this result, is it, so I guess you're going to be using this TQFT picture that you gave. There's this algebraic description of this Euler structure trivialization, this home class, I guess. Is that, so is there like a more geometric intuition here why the Whitehead torsion appears?
So the proof actually doesn't. So I would say the main result is kind of split into two steps. So first of all, you want to understand how the loop coproduct changes. So what we explain is that you can split the question into first understanding how this Euler structure changes, how this trivialization changes, and then out of that, there's some complete algebraic computation showing that that's how the loop coproduct changes. So really the meat of the argument is how the Euler structure changes. The rest is some TKFT or algebraic arguments, which are fairly straightforward. Now, the way to show that the way the Euler structure changes, what we use is, so this Whitehead torsion is related to, so simple homotopy types are about being able to write your space as a union of disks. So if you have a finite CW structure, your space is a union of these cells. So basically, you have this Euler structure coming from the theory of Whitehead torsion, so this simple homotopy type. And then there's a totally unrelated Euler structure that comes from intersection theory, which is the model of this Von-Schrank-Thom collapse of diagonal. So what we show is that the one coming from intersection theory is kind of compatible with gluing of cells. And for a single cell, there's a unique Euler structure. Just because the loop space of a disk is homotopy equivalent to the disk. So if you can show that the one coming from intersection theory is kind of local in an appropriate sense, it's kind of, if you have a cell decomposition, then it behaves well, then it has to be the one coming from Whitehead torsion.